All right. Hi, everyone, and welcome to this session titled The Glorious Art of Breaking Things, or an introduction to chaos engineering. But that doesn't sound even remotely as interesting, right? Oh, let's see. That was the wrong window. I'm bound to get this right at some point. There we go. You should now be able to see my presentation. So let's get started. Okay, so my name is Simon Aronsson, and I'm a developer advocate at a company called K6. And as part of my role, I try to help developers build resilient and robust systems through performance testing and chaos engineering and other reliability practices. And I'm organizing a couple of different meetups and things like that, and try to be involved in the reliability community. So feel free to reach out if you want to know more about chaos engineering, or if you want to get some suggestions on where to go to get more information or to participate in the chaos engineering community. Um, if you want to get in touch after the talk, as I said, you'll find me on Twitter, where my handle is 0x12b. So now, to get started, let's start off a little bit slowly by talking a bit about what chaos engineering actually is. And while it's really fun to think of chaos engineering as just breaking things because it's so fun to break them, that's not really what it is about. We don't just want to burn things because it's cool that they burn. It is cool that they burn, and I at least enjoy that as well, but that's not the primary reason. Uh, we want to make sure that all the effort we've put into making our systems as stable as possible actually work as we intend them to when we're off in production. And the formal definition of chaos engineering, taken directly from the principles of chaos engineering, is that chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. And that might sound a little bit too formal, so let's try it in less formal language. Well, we're trying to break things on purpose, in a controlled manner, to make sure that they won't break later when we're no longer in control. For instance, when we are sleeping during our on call. And according to Jim Scheibmeier, who's an analyst or senior principal analyst at Gartner, the reality is that if we're not doing chaos engineering, then or avoiding doing chaos engineering is actually the equivalent to doing crisis engineering. And I think that he really hits the nail on the head with that sentence. If you systematically and empirically try to expose weaknesses in your systems, in your infrastructure or your architecture, you'll obviously be a lot better equipped to handle that when the real incident occurs. Yeah, and as Lucas is writing, some men just want to watch their instances burn, and I guess that's right as well, for sure. So, what I really want to emphasize here is that we want to test for the unknown unknowns, because unknown unknowns are really hard to prepare for. So, simulating stormy weather conditions using real world circumstances are most likely our best bet to exploring these territories. If we already are aware of critical weaknesses in our systems, we need to fix them first. There is no real point of testing for something that we already know. For instance, if we only have one database instance, uh, then we already know that if it were to fail, then we'll be totally out of service. So there's really no need to design an experiment that will tell us just how screwed we are if that database instance goes down. Sorry. Yeah. And as with most DevOps practices, it's usually a good idea to try to start small. And until we get a good hang of what we're doing, we probably shouldn't get anywhere near a production environment with our chaos experiments. So the goal should probably be, for most of us at least, depending on the sector you're working in and the regulations there, that we want to do chaos engineering in production at some point. But a staging environment usually has enough similarities with the production environment to be able to serve as a dojo of sorts, where we can get started, we can practice and sharpen your skills just as we would if it actually were a dojo and we were practicing martial arts. Because causing a real outage and not having any idea of how to get it back to stable, or maybe even how to cancel the experiment, just watching as it ticks towards disaster, right? With more load or more failures building up every second. That would have devastating consequences, uh, both to revenue, but for sure to morale as well. You don't want to be the person sitting in front of the computer running the experiment and just watching the whole production environment burn to ashes. So try to keep this in mind, that even as we start to progress towards bigger experiments in production, as chaos engineering practitioners, we need to ensure that the effects of our experiments are minimized and contained to as big an extent as possible. This does, of course, in no way mean that we shouldn't be allowed to do experiments that have short-term negative impact. Rather, that the impact should be as small as it can possibly be by still giving us the assurance or confidence that we need to build in our system's reliability. So let's try to have a look at how we go about actually performing chaos engineering. The process is quite simple and actually only consists of 4 to 5 steps depending on how you view it. And there is a pattern to these steps. The first 3 steps, define the steady state, build a hypothesis, and designing an experiment, they're all about planning. And this is probably where most of your time actually will be spent. So there is actually a reason for this, because the more detailed and thought through your plans actually are, the more likely you are to uncover something of value and to not have the errors cascade to your users. For instance, poor planning usually just leads to a lot of manual work and little to no valuable insights, except that we probably should have planned better. So first, when we get started with this, we need to define the steady state. And that is as in, how do our systems behave under normal circumstances? So before we're able to actually measure whether something breaks during certain conditions, we need to know how it behaves when it's business as usual. And this could be things like a number of instances of a replicated service in our Kubernetes cluster, the CPU and memory usage of our application servers, what the concurrency limits are, or whether whatever else you can think of that will let you know where that conditions actually are stable. I know Nicole, who's also in the chat, is usually really good at this. So I usually go to her when I need inspiration for these kind of steady states. Next up, we need to build some kind of hypotheses that we may use to determine if our chaos experiment was successful or a failure. And using this hypothesis, we will later be able to draw conclusions from the actual outcome. The hypothesis itself should be written in such a way that we build upon the expectation of a positive outcome. A hypothesis that expects the outcome to be a failure. Instead of actually doing such an experiment, we should take that as a prompt to take additional actions to strengthen our system's resilience prior to actually exposing it to turbulence. So in short, our hypotheses should be formulated to confirm the reliability of our systems rather than proving that they're already broken, right? As an example, if one of the containers responding to API requests fail, the performance of our system will not be degraded by more than 10%. That's actually a lot more reasonable as a hypothesis than, for instance, if the container responding to the user API requests fail, our system will be unavailable until a new one is in place. So try to make the experiments, or rather the hypotheses, expect a positive outcome for your experiment. And then once we have our hypotheses down, then it's time for us to actually design an experiment that simulates the circumstances that our hypothesis describes. If we use the positive hypothesis example that I just mentioned regarding the 10% degradation, this would mean that we need to inject chaos or failure into our cluster, causing one of our API containers to fail or to terminate, and then measure what effect that has. And that takes us to the next step, measuring the outcome. Because the execution, as I said, is the smallest part of this life cycle. We run the experiment and we measure the outcome. And before we start to run the experiment, however, we need to make sure that everyone in our organization has been informed about the experiment, or at least everyone that has any stake in your experiment. So it wouldn't be that good if we suddenly just noticed on our dashboard that our system that we're maintaining or that we're operating is down in all our different load zones or geographic zones, right? We want to be aware that someone is doing something to our system, and we want to give others that possibility as well. And while our systems are affected by the failure that we inject as part of our experiment, we also want to probe the system to make sure that our hypothesis still holds true. For our API example, this would mean exposing the system to traffic similar to what we have in production, making sure that the degradation in terms of latency or request failures indeed stays below 10%. And for other scenarios and hypotheses, it might make more sense to probe for error rates in system logs, or measure resource consumption, or check for data corruption. So, depending on what you are formulating your hypotheses around, that also affects what kind of probes you will do to ensure system stability. Uh, and if our system at some point strays away or drifts away from the steady state, then we immediately need to terminate the experiment and let the systems recover either automatically or by performing rollback actions. Because once we know that it's actually not able to survive our experiment, or that it will drift away, then our experiment is effectively over. We don't need to push it further just to see exactly how bad it breaks. That's usually just that could be fun, and you can do that in a staging environment. But in production, you want to keep it as contained, and you want to keep the impact as small as possible. So once we know that it fails, we just quit the experiment and try to get it back to stable instead. And this is actually quite interesting, because the harder it is for us to make our systems drift away from the steady state, the more confidence we get about our system's reliability. So, by doing continuous chaos experiments, we build a service that is harder and harder to make drift away from the steady state, and thus giving us more ease of mind or more confidence that it will be able to survive turbulent conditions, even as we maybe are off to sleep during on call, or not watching it closely. So, for me at least personally, it makes a lot of sense to do these practices to make sure that it's that we get the confidence that we need. And last up, now that we've built our hypotheses and designed an experiment and measured the outcome of it, we need to make sure that we address any issues that we find as part of the experiments. And until this is done, there's really no reason to run any more experiments on that service or that system, because we already know that it's broken. So now we need to take some time to put in some effort to make the systems not as susceptible to that failure as they were when we did the experiment. And once we've done that and strengthened the reliability of our system, then we just repeat the process all over again. So we will be doing a demo here where we'll be using Chaos Toolkit, which is a open source tool for doing chaos experiments. There are of course many other tools. For instance, the paid tool Gremlin, or you could use Litmus Chaos or Powerful Seal, or even our own K6 Chaos. But In this case, we're going to use Chaos Toolkit because it's a good starting tool, because it's quite easy to use and gives you nice visualizations, or rather nice tools to measure the outcome while not needing that much setup to get started. And how will this work in practice then? Well, you as the tester, or the scientist, if you will, that's probably a funnier way to think about it. Design an experiment based on a hypothesis, as we said, and then utilizing drivers that are available in Chaos Toolkit, we'll be able to connect to our resources and inject different kinds of failure into our system to make sure that the degradation stays within the bounds that we've defined. And if we are able to perform all the actions that we've defined as part of our experiment while still staying within our boundaries or our error budgets, the test is considered to be successful. If not, it's considered a failure. And the result, regardless of outcome, can then, using plugins, be sent to a different variety of servers, like to your Slack channel, or to an external visualization system like Grafana, either for storing or for producing notifications. So that really gives us the possibility to follow up on whatever the outcome was and use the data gathered during the experiment as a basis for finding things to fix. We'll also get a journal created locally on disk that we can use for the exact same purpose. All right, so let me just switch over to Visual Studio Code and we'll get started with the demo. There, I hope everyone can see my screen now. All right, so I've gone ahead and done some preparations here. Sorry. Let's start off by having a look at our cluster, our Kubernetes cluster. As you can see here, we have 5 different web servers that are all running the same image as part of a replica set. And these are the web servers that we will actually test. We also have a load balancer that will help us balance the the actual requests between the pods that we have available. And we have an ingress connected to a external domain name, and that we can use to access these servers and these pods. So what we'll be doing in this experiment is that we'll try to terminate a random pod and at the same time run some load towards the service or the ingress, making sure that it stays available or within bounds as we run our experiment. So first off, we're gonna add some kind of version to our experiment. So this will be our 1.0.0 experiment. And then we'll give the experiment a title as well. We're gonna name it, let's see, chaos 0x12b.com load balancing test. All right. And then we'll add a description, which will be our hypotheses expressed in a more human readable way. So when terminating a random pod from a replica set containing API servers, there should not be any dropped or erroring requests while the service recovers. Or rather, let's make that, we'll just keep it as that for now. Maybe we need to tweak that later. Then we're going to add some tags to our experiment as well. And these tags, they are used to explain the areas or the components or what have you that the experiment actually concerns. So I'm going to go ahead and add Kubernetes and pods, replica set, ingress, error rates, and HTTP. That should fairly describe what we're going to do in this test. Let me just make the terminal a bit smaller as well so you can see a bit more of my screen. All right. So now that we have our title, our description, and some tags that describe the test or the experiment, we're also going to add an explanation of what this experiment contributes in terms of um, in terms of confidence around our system. So let's add a YAML tag called contributions, and then we're going to rate how much this contributes to confidence in reliability. And I would say that that's a medium in this case. And we're also going to assess how much it affects security. Thank you, Nicole. Yes, there shouldn't be any draft or erroring requests. Otherwise, it would be quite a bad experiment. So back to the contributions. Security. I think that our experiment won't have any input in terms of security or any addition to the confidence. But it will add some confidence in terms of scalability. So we're going to set that to low. So this is the metadata around our test. Now we also need to actually define the test or experiment by setting up the steady state hypotheses as well as the actual methods or fault injections that we'll use throughout the experiment. So let's start by setting up the steady state hypothesis. And we'll give that a title. So API is alive and healthy. Great. We'll also add some probes to that steady state hypothesis, and the probes will make sure prior to and after we've injected chaos or failure that we still are within the steady state hypothesis. So it's a good way to make sure it's our system is still behaving as we expect it to. So this will have a type of probe and it should have a name as well. And we'll call it API is responding with HTTP status 200 under load. And we'll set the tolerance to true, as in we only tolerate that this assumption is true during the test. For other kind of probes, there might be other types of tolerances that you can set, but in this case, we're going to go with just true, that we expect it to stay within the bounds. We'll then create a provider for this probe as well of the type Python. So that's actually quite cool with Chaos Toolkit. You'll be able to create your own either shell functions that you can use or shell scripts as part of your experiment as probes or as methods, or you can actually write your own adapters or drivers in Python and ship them so others can use them as well. And in this case, we will use Python. And we're going to use a module that I built myself called Chaos K6. And we're going to use the module probes from that module or from that package. And this is a HTTP function, or we will use the HTTP function of the probes module. And we'll also pass some arguments to that function. So the endpoint that we'll be testing is chaos.0x12b.com. In a real world scenario, this will probably be an HTTPS call, but for the sake of this demo, we're trying to keep it simple. So it's just a regular HTTP call. We're going to use the HTTP method get. And we'll be expecting the status for our call to be HTTP status to be 200. We'll do this with 10 concurrent virtual users. So we're basically telling our load generator that we want 10 users to be performing our action at the same time. And we want them to do this for a duration of 10 seconds. So for 10 seconds, our virtual users will just hammer this endpoint with as much requests as they got time for, and just make sure that each request gets an HTTP status of 200. We're also going to add a debug flag just to make it possible for us to view the output from K6. But if we were to run this in production, we would just probably turn that to false instead to make it less spammy in our logs. And we'll also add a header that says that the content type should be application JSON. All right, so this probe that we've added, it should make sure that our HTTP API actually behaves as we intended to during the test. So let's go ahead and run this before we continue. I think we need to also add a empty method key for it to work. Okay. Yeah, we're back to the method part, right? So I'm just going to do it like this. All right. Make this a bit larger. And now we see that our experiment has valid syntax, and we're running the experiment load balancing chaos.0x12b.com load balancing experiment. And we're using the steady state strategy default, and then we could have more steady states, but in this case, we're using the default. And the rollback strategy default as well. And the steady state hypothesis is that the API should be alive and healthy. And we're then running our probe, executing some requests, like 32,000 requests, and we have 0 failures. So far, so good. And we then run it once, and once that's done, we inject our failures that we've defined in method, which is currently 0. So we just run the steady state hypothesis once again to make sure it's still valid after the experiment, and then we're done. And so far, everything works, but we've not started doing any actual failure injection yet. But before we actually do that, we're going to add another probe as well. So the second probe we'll be adding is a probe that will help us check whether the pods recover in a timely fashion. So we have another probe that will name count pods. The tolerance for this probe will be 5. So we're expecting our pods that we showed earlier, they should be 5, right? So that's the normal circumstance, that we have 5 pods in our replica set. We'll add the provider for that as well, and it will be a Python provider this time as well. And the module will be chaos k8.pub.pro. And the function we'll be using is count pods. Arguments for this one as well. So let's set the namespace to chaos demo, because that's the namespace that we are actually using. Chaos demo. Yep. All right. And we'll add a label selector to help us pick what Kubernetes pods we want to look at. And this will be run equals chaos nginx. We want the face of our pod to be running. So if it's terminating or if it's starting, it should not be considered a valid pod for this experiment. It should be in the phase running. So with that, let's try it once again. So we check that the load is still behaving correctly, and then I don't know if you were able to see that, we count the pods, and the steady state hypothesis is met, meaning that we don't get any errors from the HTTP calls, and there are actually 5 pods. And then we repeat it again. Now, let's add some failure to this as well. And while this in no way is the best or the most valuable failure injection that we could do, it's one of the most obvious. So the one we're going to use is to actually terminate a pod. But we might as well use failures like adding latency or making a upstream system unavailable rather than just affecting the HTTP API servers directly. But we'll go for that in this example. So here we'll add an action to our test, and we'll call it terminate nginx pod. It will have a provider of the type Python as well. And it will be in the chaos Kubernetes module this time as well, but this time it's an action, and the function we'll be using is terminate pods. We'll give that some arguments, the namespace yet again, and the label selector. And a name pattern for which it will use to pick what pods it's going to kill or have as candidates to be killed. And this will be a regular expression. Let me just find the correct keys. Where we want them to be named chaos web server followed by something. This should match with what we have here. Yeah, so chaos web server followed by something. We want to give the pod a grace period of 2 to allow it to actually finish any ongoing request before it's killed. Depending on what we want to measure, we could set this to 0 as well, making it terminate instantly, and we'd get a better understanding of what would happen, for instance, if the server or the data center went out of power or something like that. But for this demo, we'll be using a grace period to make sure that they are actually able to finish any in-flight requests before terminating. We want the pod that will be terminated to be picked at random, and we want the quantity to be 1. And we'll also set the mode to fixed. So we'll run our steady state, we'll terminate a pod, and then we'll run our steady state check again. And that will be the whole experiment. So let's try that again. Right, and here we can see that we're running our action to terminate the nginx pod, and then we are running our steady state again, and everything is still good. If we were to up this to 2 pods being killed instead of 1, it would probably no longer be able to satisfy our steady state. Let's have a look at how that turns out. Yeah, and as expected, we can see that if we kill 2 of our 5 pods, we are no longer able to stay within the tolerance that we've defined. So then we know that we have something that we need to address within our system to make it more reliable. In this case, for instance, it might be a good idea to have a look at whether we can make our load balancer aware of which pods are functioning on route, using, for instance, health checks or something like that as a prerequisite to route a request to a certain pod. We could also use some kind of retry logic as part of the load balancer. So, for instance, if we get a failure from one of our pods when we try to do a request, we'll just pause for 100 milliseconds or something and then retry it using another pod. And that way, while the user would have some more HTTP request duration, they would still get a successful response, hopefully making the experience a little bit less frustrating. And now that we've run our experiment in a couple of different variations and seen that we can make them pass and we can make it fail as well, then we can have a look at the journal that I mentioned previously or prior to this. And here we can see it follows almost the exact same format as our experiment, but with some added metadata for the test run that we actually did. So we can, for instance, see that, let's see, we'll roll down a bit. Before running the experiment, our steady state reported the output true, as in it succeeded, and the status was succeeded. They took 11 seconds to run, and the tolerance was met. And we ran it with this configuration. We can also see that the output of our pod count was actually 5, and that was quite fast to get as well. So the tolerance was met. We can then also have a look at how the steady state looked post the failure injection. And that this is actually quite interesting because this was not met, right? So we can see that after 3.7 seconds of the first probe in our post-experiment steady state, we actually failed. We were no longer able to serve requests with 0 errors. So this could be used as an analytical tool to make sure that we understand what is going on and why. All right, so that was the demo. Let's go back to the presentation. There we go. All right, so now that we've run our experiment, we need to do some kind of debrief to make sure that we actually capture the information that we've gathered and make something out of it. And depending on the size and scope of our experiment, because this was a very simple, very small experiment, it's not too uncommon to feel fatigued. So at this point, I'd recommend taking a short walk, maybe grabbing some fresh coffee or calling your kids because we're not entirely done yet. And usually we want to do this as part of the experiment session to make sure that it won't be left aside because other priorities are asking for our attention or that we just forget about it. So immediately after running the experiment, let's evaluate the results. And we'll do that as part of measuring the outcome of the experiment, as I said. And this is right after the planning, the most important exercise or the most important activity of this entire exercise. So make sure that everyone that was part of the experiment actually stays and participates on this as well. And I've shamelessly borrowed some kind of questionnaire from the Slack team that really resonated with me that they use for their debriefs. And first off, how long did it take for the error to be detected? In our example, we could see that after terminating the pod, it took us 3.7 seconds prior to the experiment being aware that there was an issue, and then it terminated as we expected. But we can ask ourselves, is this good enough? Can we speed this up somehow? Is there anything we can do to make the error detection more instant? We can also ask ourselves, how long did it take until the system recovered? And in this case, it's actually hard for us to know because we only run the steady state once. So here we would need to add something else on top of this to make sure that we capture what happens after the test has finished. Maybe we should add some sleep before doing the steady state check, but then we would miss other things. So we need to play a bit with this to make sure that we find a experiment that is suitable for also measuring when the system recovered. Because if it takes, for instance, 5 minutes for a web server to recover after injecting some kind of failure is detected, and after injecting some kind of failure and the failure has been detected, that's likely not good enough. I mean, we want to know that our system recovers faster than that. We also want to know if this affected any users. And depending on the answer to the previous questions, this will more or less likely be the case. In what way did it affect our users, and how can we be sure? Is there anything we can do to make a yes here into a no instead? For instance, as I mentioned, we could add some kind of retry logic to make this a yes, or a partial yes at least, given that they still will have some kind of additional latency or additional response time. Did the recovery require any manual intervention? If so, we need to document exactly what that was, when, and why. And before running the experiment again, we should really make sure that we eliminate these steps and investigate whether we actually need to do them, or what we can do to make them go away. And if we can't do that, we need to at least make sure they're well documented and available to the on-call team. And last but not least, how can we improve our monitoring and documentation based on the findings? Was the error visible in the monitoring? Because a lot of times it isn't, right? We think we have a monitoring in place that shows us what we need to know, but it shows us what we need to know based on our prior knowledge. So when we do an experiment, we usually find out something new that we could have measured or monitored for. And then we need to add that, and also add descriptions of how to interpret that result into our documentation for the on-call team or for ourselves. And are there any additional steps we can take to improve this further? All right, and that was the whole talk. I hope you found it as fun as I did, and we'll now be going over to Q&A. Unfortunately, my camera seems to have given up, so you'll have to deal with my voice, but that should probably be okay as well. And we have one question from Dennis Medinsky, who asks, how would you set up more complex step-by-step experiments? For example, scenarios of making a purchase, log in, add item to a cart, proceed to checkout, etc. Yeah, in this case, because that question really goes to the K6 module, I think, of the chaos experiment, I would write my own custom script for that. So I would write a K6 script that does all of these actions and use that as my probe rather than the single endpoint probe. And then we have another question. Could you share a link to the repository with code which you used in your demo, please? Yeah, sure. I'll try to do that as soon as possible after this presentation. I don't think it's available right now on GitHub, but I'll make sure to add a link somewhere where you'll be able to find it for sure. Do we have any more questions? All right, then that was the whole session. Thank you so much for joining me, and hope you'll enjoy the rest of the conference. And feel free to get in touch either on Twitter, where I'm 0x12b, or on LinkedIn, or via mail at sime@k6.io if you want to discuss anything chaos engineering or reliability related. Have a great day. Bye.